Chiara from KIT, and she will talk about how to efficiently do next-to-next integral computations in QCD. Please.
Thank you very much. In the next 20 minutes, I will try to convince you that inference singularities are interesting and why we need a subtraction scheme. So after the talk by Fabio, I think I don't have to explain you that LHC continues to confirm the standard model, and that's why it's crucial to provide higher order prediction and high precision theoretical prediction to compare with experimental data. And from this plot, we can really appreciate how much effort has been devoted into NLO hadron collider calculations, and MQBLO. Some MQBLO calculations are already available. And this has been possible also because we have a strategy to deal with the infrared singularities. Is indeed a fact that infrared singularities affect both the virtual correction and the real radiation, but in two different ways. So loop correction are affected by infrared singularities that essentially come from the loop integral, while phase space, real radiation is in principle finite in d equals 4, but it is affected by phase space singularities that become manifest as 1 over epsilon pose just after performing the phase space integration. So we have a very powerful tool to, let's say, deal with the infrared, which is the KLN theorem, which essentially states that the combination of virtual and real correction for a subset of observable is infrared finite, so is protected by infrared singularities. This is not the only weapon we have. So another important property is that infrared singularities are in some sense universal. So in particular, regarding the virtual, we know that in dimensional regularization, the explicit pose of 1 and 2 loop amplitudes are independent on the hard subprocess, meaning that I don't have to compute every time this loop correction to know which is the inferent content of the virtual. For the real radiation, this is slightly different. So if we focus on this very simple Feynman diagram and we write down the Feynman rules, we immediately realize that there are two different regimes that can lead to a singularity. And in particular, these are the soft regime and the collinear regime. So luckily, also for real radiation, we have a remarkable degree of universality. So we know that real matrix elements factorizes some universal functions and a lower multiplicity matrix element. And I will refer to these functions as kernels, so infrared kernels. So at this point, I think it's natural to ask the question, where you have the KLN theorem, you have universality, where is the problem? Well, the point is that I would like to extract the infrared singularities of the real matrix element without integrating over the phase space. And the point is that I want to have fully differential results. So at this point, the second natural question is, can I design a procedure to deal with the infrared in a full generality? And in principle, I think that this universality that I just described may suggest that the answer is yes. Although the practical implementation of this yes, we can do it, is highly non-trivial. So there are two families of possible solutions, and I will focus on the so-called subtraction. And the core procedure of subtraction is really simple, at least in theory. So we have a quantity I, and this quantity is, we know that is finite for epsilon going to 0, but it depends on an integral which is too complicated to be computed analytically. I know where the singularities of this integral are, so a possible strategy is the following. I can subtract to the initial function its limit in the singularity, so in x equal to 0, such that now this term is finite as epsilon goes to 0. At the same time, since I want to leave the initial problem unchanged, I have to add this object back. But at this point, it's easier to solve this integral and to extract the pose that can be combined with the last term. This F0 is what we call counter term, which in practice can be really quite involved to define. So from a more physical perspective, what I have is a real radiation and a phase space integral. I don't want to compute it analytically, so by hand, because it's too complicated. I can subtract all the singular limits and get something that is now finite. I can compute it numerically, so using a tool, an algorithm. And then I have to add the singular limits back. But now this term can be computed analytically. It can expose its pose that I can cancel with the pose coming from the virtual. So this is a bit the theory. In practice, as I mentioned, is a very non-trivial. So at the next to leading order, we have two main schemes, the so-called Catani-Seymour scheme and the FKS scheme. And in principle, they are very well tested. And the problem at the next to leading order can be solved, can be considered solved already 20 years ago. So why we are still talking about subtraction? Well, the point is that at NNLO, the problem is so highly non-trivial that we have different schemes, and we are still looking for the best possible subtraction procedure, meaning that we are still working to design a method able to accomplish all these requirements that I listed here. So what about what we are doing? So essentially, the idea is, okay, the problem is next to next. What we would like to do is going back at next to leading order and design a method identifying precisely the properties that we want to export at NNLO, and also identifying the methods we can use to achieve, let's say, a very simple scheme with the possibility to also investigate with the same scheme NNLO. So the story is always the same. So I have a combination of virtual and real in order to regulate the real metric segment singularities. I can add a counter term, and then I also have to integrate over the unresolved phase space in order to have essentially an identity moving from this formula to this formula here, where now this term, as I mentioned before, is finite, can be computed numerically. And by integrating over the unresolved phase space, I am also able to cancel the virtual explicit pose. So of course, I don't want an arbitrary complicated counter term, otherwise it would be impossible essentially to export the idea at NNLO. So I'm trying to design a method where the counter term is minimal and it's defined in such a way that can be integrated over the unresolved phase space analytically and with standard techniques. So now I will introduce a couple of ingredients. And the first one is a phase space partitioning. So why we need it? It's not too difficult to guess. Essentially, starting from this process, if I plot the Feynman diagrams contributing and also the Feynman rules, I can immediately realize that there are several possible singular limits. And in particular, I have two different collinear limits that appear in the real metric segment. So since this problem, let's say, is difficult, I want to split it into sub-problems that are separately easier than the initial problem. I can do it by introducing sector functions. So essentially this quantity W31 and 32. And what is the job of these sector functions? So essentially in each sector, what I would like to do is the following. I want to dump one singularity and to enhance the other. And in the other sector, I would like to do exactly the opposite. So essentially, the goal of sector function is selecting in each sector the minimum amount of singularities, because it's easier to treat them. The second ingredient is a momentum mapping. So why I need it? essentially because, as I mentioned, I don't want to integrate over the full phase space. So I need something to, let's say, split the bulk resolved phase space from the unresolved phase space. And moreover, I would like to, at each step of my computation, handle a kinematics where all the momenta are on shell and momentum conserving. So I don't want to focus on the details. The crucial point here is that a mapping is essentially a combination of momenta that I will label with A, B, and C. And the way and which momenta I choose to combine is essentially free. So I can choose, this is one of the tricks, I can choose A, B, and C, so the momenta to combine, in a smart way. So in a way that I can exploit to simplify the integration. So let's discuss a little bit the recipe. So now I have a simpler problem, so I can focus on a single sector. In this sector, I know which singularities contribute. So it's not difficult to design a counter term as the collection of all these singular limits. And the bar essentially explains that I'm implicitly using a mapping. So from a more intuitive point of view, what I'm doing is taking my real radiation, choose a specific sector. What I'm doing now is introducing a counter term such that now this object is finite. And the last step is integration over the phase space. So this is a non-trivial step. And the crucial point is that in order to simplify the integration, I choose my mapping. So I choose the momenta A, B, and C in agreement with the kernel. So in agreement with the singular limit I'm considering. So in other words, essentially what I will do later is parameterizing the phase space in agreement with the mapping and therefore in agreement with the kernel. The crucial idea is that I don't want to use Cartesian coordinates to integrate a cycle, and I don't want to use polar coordinates to integrate a rectangular. So focusing on the integration, what I'm doing is essentially parameterizing this radiative phase space using essentially the same momenta that I have chosen to introduce, essentially to combine for my mapping. As a consequence, what I'm doing is essentially parameterizing a cycle in polar coordinates and integrating over polar coordinates, and therefore the integration is extremely simple and can be really done in just a few steps. So the lesson is the following. I have a complicated problem, I can split it using partition, and in each sector, I can use mapping and parameterization to simplify the integration. And the crucial aspect is, okay, this mapping and this parameterization have to agree with the limits and with the singular contribution to the counter term. So the natural question is, okay, but this is next to leading, it's easy. What about next to next? Well, at this level, we have three main configurations. So we have the double virtual, the real virtual, and the double real. And once again, I will focus on the double real. So why NNLO is difficult? Well, one of the reasons is that if I simply plot one of the possible diagrams and the corresponding Feynman rules, I really can understand that there are many configurations that can lead to a singularity. And one of them is the triple collinear limit, so when all the partons become collinear at the same time. But this is not even the end of the story, because there is not just one way that three partons can become collinear. So I can also have strongly ordered configurations where two partons are more collinear than the others. So at this level, I also have strongly ordered configuration, not only for the collinear component, but also in the soft regime. So it's definitely evident that at this perturbative order, I have really a lot of different limits. I have a lot of different overlappings between these limits. So for example, I have a double soft limit, but also the corresponding strongly ordered limit where both the gluons are soft, but one is much softer than the other. What is the trick?
Chiara, sorry, you have 5 minutes.
Yes, perfect. So the trick is again the same. Take a complicated problem, split it into sub-problems, which are in principle easier than the initial one. So in doing this, what I can do is introducing again partition functions, and in each partition I can really recognize 3 different counter terms that can reduce the real matrix element to a finite object. And despite this complexity, the physical interpretation for these counter terms is quite easy. So let's focus, for example, again on the double soft limit. What I'm doing is collecting the single unresolved configuration into this K1. And single unresolved configuration mean that only one of these 2 gluons is soft. I also have to subtract the case where both the gluons are soft at the same time, so in the same way. And I have to, let's say, correct for the overlapping between these 2 configurations families. So the case where both gluons are soft, but one is softer than the other. So what I called before strongly ordered configurations. So of course, this is not the last step. We also have to integrate over the corresponding unresolved phase space. So among all these counter terms, the most difficult one is, let's say, K2. So the most difficult part of the job is computing I2, which is the integral over the double unresolved phase space of the counter term corresponding to the double unresolved configurations. So essentially what I explained before, of essentially the configuration where all the partons are unresolved in the same way. So the next 2 slides are just, let's say, there to give you a bit the flavor of what is going on, so what we are talking about. I really don't want to go into details, so it's just really to have an idea. So here I just put the double soft limit and the triple collinear limit in the case of 3 gluons. So we see that in principle is something not trivial. So we are not integrating x over dx. So we have different structures, and these kernels have to be integrated over 6-dimensional phase space. So the crucial point is that using the trick I explained before, so adapting the mapping and the phase space parameterization of these on these essentially different structures, I can really simplify the integration and obtain a result that is incredibly simple with respect to the initial problem. So the result is essentially an expansion in epsilon, where the coefficients are really just numbers. So for me, it's really nice to see a very simple result for a very complicated problem. So I just want to conclude just sketching the general pattern of our subtraction. So the double virtual, the real virtual, and the double real are the initial objects. I have very briefly discussed the counter terms K1, 2, and 1, 2 for the double real. And I also have to add a counter term to treat the real radiation singularities of the real virtual component. And here we can see also all the integrated counterparts. So despite the very high complexity of the problem, the solution seems to be quite simple, or at least quite compact. So my take-home message is the following. So phenomenology requires high-order correction, and this correction can be, let's say, investigated knowing how to deal with the infrared. One possibility is subtraction, and the scheme we have implemented in Torino, I think, is a good, let's say, option. And very recently, we have completed all the computation of all the integrated counter terms. So at this point, all the building blocks of this scheme are available. And thank you for your attention.
Thanks a lot, Chiara. It's a very, of course, always a technical endeavor, right? But you made a clear effort to be able to appreciate it in its complexity and richness. Thank you. So we accept questions in case there is. If yes, Elijah, please.
Yes, I'm curious to know which of the 5 criteria that you listed in one of the first slides is satisfied by your scheme.
Well, in principle, all of them. Then
Okay.
in practice,
very good.
No. Well, so just a second, I just want to have them here. So in principle, I think this scheme is physical transparent in the sense that looking at the counter terms is not difficult to trace what they are. So which singularities are they subtracting, how they are organized. In principle, it's general in the sense that we have this scheme is already designed for an arbitrary number of final state partons. We also have, thanks also to Gloria Bertolotti, there is also an implementation for initial state radiation at next reading order. The scheme is fully general, and we have recently completed all the integrals, and they are all done fully analytically. So also the criteria number 4, I think, is satisfied. Then for efficiency, I think we have to first implement it. So first to provide code, differential code, and check if also the efficiency is, let's say, the best, or at least one of the best available on the market.
Okay, thank you.
Thanks.
I don't see any question right now, so I'll take the liberty to ask for curiosity. I mean, so you have seen you're using this divide et impera, right, kind of approach, right? You partition the face, and then you try to get the mappings that are giving you the simplest possible analytic results when you integrate over the counter term. Now, of course, one of the questions that you somewhat hinted to is point 2 here, right? So it's the generality, in the sense that, I mean, will you be able to handle also massive particles with the same scheme in the final state? That's one question I had. And the other one, I would like to understand what is the scaling, right, with the number of particles in the final state. So do you know already how this complexity of the partitioning scales with the number of particles at the Bohr level and in the final state?
So, so massive particles are on our to-do list. So probably in principle, probably we can really adapt all the main ingredients I try to discuss also with the massive partons. Because in principle, with massive partons, we can also try to introduce sector functions, mapping. Of course, they are different. And of course, probably the phase space integrals will be more complicated. Honestly, I haven't tried to approach this problem yet. I don't know if others are working on this specific in generalization or not, but I think it's doable. I think it's doable.
And do you know do you have any idea by now how it scales in complexity? I mean, it's like, this growth become unmanageable for some n in the final state, or is you think this will not be a problem?
Well, I don't have let's say super local answer for that, in the sense that it would be also great to first see the performance of the numerical implementation.
Yeah.
So at this level, the point is that we have all the ingredients. We are still working on the general proof of the cancellation of all the singularities. So before knowing exactly let's say, how efficient is the method, I think we should first prove in full generality that the scheme is actually working, and then, let's say, evaluate the performances.
And then you worry about the rest.
Of course.
Okay, okay, very good. Okay, so this is the last call. If there's anybody who wants to ask a question, it's a good moment. If not, we thank Chiara again. Thanks again, and